The latest version of ProtoTwin includes a wide range of new features, so let's dive in. We've added a new robot controller component. This allows users to effortlessly create simple robot programs through the user interface. The integrated solver can handle any type of industrial robot, including those containing closed kinematic loops. You don't need to provide the inverse kinematics for the robot. The solver handles everything for you automatically. Once you've set up all the joints for your robot, you just need to add the robot controller component to the top-level entity. You can then select the tool center point, or TCP, for your robot and start adding instructions. We support a wide range of instructions, including joint moves and linear moves. Here we demonstrate adding the instructions necessary to perform a pick-and-place operation. The move instructions just require you to specify an entity which represents the target for the robot. You can set the default speed and acceleration for the robot, or use the set speed instruction to modify the speed during the execution of the program. With all the movement instructions complete, it's time to interface the robot with the wider simulation. We do this by adding an await signal instruction so that the robot waits for the sensor to be blocked before attempting to pick the box. You can drag instructions in the inspector to reorder them. It's also worth noting that when we run the simulation, the instructions are highlighted as they are executed. Okay, finally we will use a set signal instruction to enable the suction gripper immediately after moving to the pick position. We'll then use another set signal instruction to disable the suction gripper immediately after moving to the drop position. And that's all there is to it. One final thing to note is that the robot controller can execute scripted programs. This allows you to create advanced programs for things like tracking and picking moving parts, or for picking parts where the position isn't known beforehand. We've added a new component for modeling springs. This component works by turning any prismatic or revolute joint into a spring. Here I'll start by adding a prismatic joint to a regular box with physics. We can configure the axis for the joint by selecting the top surface so that the box is allowed to move up and down. Now all I need to do is add a spring component through the inspector and select the joint to which the spring should be attached. The box falls to the floor as before. Let's increase the stiffness coefficient of the spring. Maybe a bit more. Okay, now let's dampen those oscillations by increasing the damping coefficient. If I quickly switch over to navigate mode, then I can interact with the physics by dragging my mouse. Lastly, if we switch back to edit mode, we can look in the advanced category to set the yield displacement for the spring. This allows us to simulate plastic deformation, which can be useful for modeling the folding of cardboard, which you'll see in just a few seconds. You can now record a sequence of frames to the GLTF format. You just need to select the desired frame rate from the list of options, hit the button to start recording, and then play the simulation. ProtoTwin will immediately start recording the frames in the background. I'll let the simulation progress for a while so that it can record a few seconds worth of frames. Once complete, you can import these frames into third-party software, such as Blender, which can be used to render photorealistic videos. Note that we use springs in the simulation of a case erector machine, which allows us to model the folding of the cardboard. Okay, to finish up, we just hit the stop recording button and save the frames to disk. And here's a short clip of the end result. We've rendered a few videos now, so I'll play just a very short montage to show you what kinds of results to expect. We've made a number of improvements to the custom collider tool. The first is that it now supports sign distance field colliders, which are dynamic triangle meshes for precise collision geometry. This incurs a high computational cost, and so they're best suited for cases where multi-convex colliders are not sufficient. We demonstrate here the ability to detect precise collisions between the threads of a nut and bolt. You can now also generate non-convex triangle meshes, which can be attached to kinematic bodies. The tool allows you to remesh the surfaces, optimizing for uniform edge length, improving the contact dynamics. Finally, you can now manually simplify the multi-convex collider generated by the tool. We show here the decomposition of a bowl into a set of convex hulls. We can simplify the collider, reducing the number of hulls, by merging the hulls at the base of the bowl. It's also possible to delete individual hulls for cases where you don't need to detect contacts in a particular area. These enhancements allow you to optimize the collider for improved runtime performance. The exported colliders can be imported into ProtoTwin, providing greater collider configuration capabilities than any other industrial simulation software.